Welcome back. It's just great to have you guys. In this class, we are going to discuss some theoretical aspects of the support vector machine, the models obtained after the support vector machine, and also how that affects the theoretical bounds we can draw from those models. So I prepared a very interesting code for you guys. I just took advantage of our previous linear SVM and I wrote a code to perform an analysis on our space. As you can see here, here I'm just building up some data set. So I'm building up the input space X and the class labels Y. Here we get the model. We just optimize the linear SVM, the linear kernel-based support vector machine. And from here, I just connected some theoretical aspects that I'm sure you guys are gonna love it. Before that, I just go back to this paper, Statistical Learning Theory, Models, Concepts, and Results by von Luxburg and Shokov. If you go to, I'd say probably to, it's like page, let me see here. Yeah, here. You go to page 22, you're gonna find this large margin bound. This is the bound we can use to understand. Here we've got the empirical risk, and here we've got the epsilon, the term epsilon. Probably you guys remember that term epsilon. If you go up, we can see how term epsilon is used in our formulation. I'm just going to go back like this. Let me show you. Yeah, maybe even before. If we consider epsilon, it measures the divergence you have in between the expected risk and the empirical risk. This is the risk we have for the joint probability distribution if we had access to every possibility for our classification task. And this is the sample error, the sample risk or sample error. So, of course, the smaller this difference is, and epsilon represents that, the better it is. Because our empirical estimation is approaching, of course, of this expected risk. So we know how our classifier just found from a given data sample is going to behave when facing the real world situations. And this represents the real world situations, the error we're going to have when in the presence of every possibility for our problem. So the closer they are, the smaller epsilon is, and the better it is, of course. If you guys haven't, read this paper, please read it. It's really, really important for this course. And of course, it's going to change your point of view on how machine learning works, how supervised learning works, more especially. That was one of the formulations we discussed a lot during this course. So from this formulation, we just decided, of course, Zapnik actually decided to call this delta, and he solved this equals to delta for epsilon, and he found actually this as epsilon. This is epsilon in terms of the generalization bound. All that is epsilon. So all that is going to measure how distant the empirical risk is from the expected risk, from the risk in the whole joint probability distribution for our classification problem. Given this is epsilon for the generalization bound, here we've got The same for the large margin bound. The large margin bound, yeah, over here, yeah. The large margin bound is the same. This is epsilon, this is the empirical risk, and this is the expected risk. So now I just decided to compute this epsilon for you guys. So if this approaches zero, I know the uniform convergence is happening, is occurring. Of course, I called C, I just defined C as 1 just to make sure this is going to be computable. And I use this as my shattering coefficient. What is that? Probably you guys remember. If you don't, go back. This is the radius of the smallest open ball enclosing all points you have in your space. So of course you've got like a bunch of inputs in your space, and consider you are at the center of that bunch of points. So you draw an open ball just enclosing all those input space points. R is the radius of such an open ball capable of enclosing all points. Of course, it is the smallest open ball. And rho is actually, this rho is actually the margin, the SVM margin. So r to the square divided by rho to the square multiplied by log of n, which is my sample size, to the square, becomes my shattering coefficient. So this is my shattering coefficient when having access to r and rho. And of course you have delta here. Delta is actually equals to this. Just going to go back so you guys can remember. So all this, yeah, all this is going to be delta. So this is delta. Delta is the probability, the upper bound for this probability. So the smaller is delta, the better it is, because we are trying to ensure a tighter bound for this probability. So the smaller it is, the less probable or less likely the empirical risk is going to diverge from the expected risk given some epsilon. So this is delta, this, okay? So I'm going to go down. That's, of course, if you don't remember, just to get back that state, of course. So here, we're going to get this as our large margin bound. So I just used the large margin bound from here on. What I did was this. I took the model, I took the alphas, every alpha belonging to the positive class and every alpha belonging to the negative class. When it has a magnitude greater than the average value for alpha, it becomes a relevant identifier. So I can use that to find the support vectors for the positive class. I do the same for the negative class. So I select which are the alphas for the negative class greater than the average alpha. Of course, those are the most important elements. So I select only those elements to compose my negative support vectors. What I did was this. If I have the positive support vectors and negative support vectors, what I can do is basically compute their distances. This function pdist comes from this package pdist. So it is capable of measuring how distant, of course Euclidean distance is the default, are the positive support vectors from the negative. So we basically get the distance, the total distance from the closest positive points to the hyperplane to the closest negative points to the same hyperplane. So I got those numbers and I decided to get the maximum value as our margin. Of course, this is not the margin, this is going to be twice the margin because it is the distance from points to points and not to the hyperplane. And the margin is the distance to those points to the hyperplane. So I had to divide by 2. That's my row. Okay, this row over here. That looks like a P. And of course, the smallest open ball is actually the greatest distance, the greatest Euclidean distance between all points I have in X divided by 2, because that's a radius enough to enclose the smallest open ball, connecting and closing all points, all space points. So I did this. I plotted our shattering coefficient function. This is the shattering coefficient function, r to the square divided by rho to the square multiplied by log of n powered to the second order. My n is going to vary from 1 to 60,000, okay? So here, I'm gonna plot this in a first chart. In a second, I will plot epsilon. Epsilon is basically all this, the square root and everything, which is shown here. I just decided to make c equals to 1, okay? So if you go back here, you guys can change. C is 1 as default, but you can change it. So we plot epsilon. Our expectation is to have this epsilon approaching 0, because that will sum up a quite small variance into our empirical risk, making sure our empirical risk approaches properly the expected risk. And at last, I plotted epsilon in a given range from 0 to 1 in terms of my y-axis. Why that? Because this is a probability. Actually, sorry, this is not a probability, but this is actually, this epsilon works actually in range from 0 to 1. Why in range from 0 to 1? Because all this formulation up here, let me go back, all this formulation assumes that my expected risk and my empirical risk are in an interval from 0 to 1. So this divergence in the worst case scenario has to be in range from 0 to 1. Okay? So that's my epsilon. And I'm gonna run this, and at last there is something very, very nice that I want you guys to pay attention. What I did was this. I returned a list with the model, with the value for r, for rho, our shattering coefficient function, and something else, our training sample size. This is way interesting. Take a look. I'm using a package called Ryakas. It's got a function yak inside that solves some mathematical expressions. Inside this, I created a mathematical expression using yak symbol. And my expression is solve a Newton, solve a Newton's function, basically, as we did before. You guys probably remember we're solving for the zero of our system of equations. That's the same here. We're going to solve for 0. So that's a Newton-Raphson method, probably you guys remember. So we're going to solve the square root. Take a look. This is square root over here. I'm going to go down. You guys can see it is here. Let me show you where it is. Probably here. Yeah. Here. So I'm going to solve this square root over here. That's our square root there. Square root up to here. You guys can notice I used 1 as c divided by n. I just set like 1 here. Could be our c that's up there, but you guys can change later. R to the square divided by rho to the square multiplied by log of n to the square. That's this part. And of course, minus log of 1 over delta, that's this, okay? Here we close our square root, and what I did was this. So for me, when this term is equals to 0.1, that's why I'm just subtracting 0.1, because Newton-Raphson method is going to solve this for 0. So I just decide to use 0.1. What that means is basically the result of all this is going to be what is the training sample size to ensure epsilon equals to 0.1. To ensure epsilon equals to 0.1. Of course, for a given delta, what is delta? Delta is over here, of course. It is defined here. I defined as 0.05. That means if my delta is equal to 0.05, this means I'll have 1 minus delta as my confidence level. That means a confidence level of 95% of this convergence, what is amazing. And this Newton-Raphson method requires what is the variable that I want to adapt and solve for. I set that as n, which is my sample size. I just decided to initiate with n equals to 100, and then I am okay when this has an error equals to 10%, just to make it faster, just to run really fast. That's why I set 0.1 as my error, as my approximation error. When I run this, I'm just going to open R, load this guy, and of course I'm going to call this function. This is actually very nice. Analysis. I'm going to get a result here, a return. This will run and build up 3 charts, 3 very important charts. This first chart here, let me increase. Okay. This is the shattering coefficient function according to Vapnik's formulation for R and rho. This is the epsilon value. As we increase our sample size here, epsilon reduces because we are converging. Because we are getting our empirical risk is getting close enough to the expected risk. Here, I have the same chart as this second, but in interval from 0 to 1, just to see this effect. Just to see that somewhere after 10,000 observations up to 60,000, we are reducing significantly the value for epsilon. Of course, the best would be some epsilon approaching 0 instead of 0.4 as shown here. But no problem. I'm going to go back. Okay. The result of this will be our shattering coefficient function. Take a look. Very nice. 61 times log of n to the square. This according to the large margin bounds. So you can compare now. You can compare different kernels found for the same problem, different solutions you have for the same problem. You can just take that as this code as a foundation to compare linear against like polynomial, kernel, non-homogeneous, homogeneous for a given scenario in terms of the shattering coefficient and something else. In terms of the necessary training sample size. You see this is 0.1 times 10 to 7. That's actually a very large sample. We need actually 1.2 million examples to ensure epsilon equals to 0.1 if our delta is equal to 0.5. That basically means, I'm going to go back just to explain once more this, because I think this is quite interesting, guys. I'm going to go back. Yeah, up here. Yeah, here. What we have is basically, in order to have this epsilon equals to 0.1, this means 10%, a 10% difference in between our sample error and the expected error if we had access to every possibility for our problem is given by some epsilon, which I decided to set it up as 10%, as 0.1. And our delta is all this. This means that in the complement of this, 1 minus this delta in 95% of the scenarios, I will have 10% of difference in between my empirical and my expected risk. I hope this was, I'm sure this is very useful to you guys. See you in the next video, okay?